welcome to this problem walkthrough. Today, we'll be exploring problem number 1099, titled 2 sum less than k. This is a fascinating challenge that tests your problem-solving skills and understanding of algorithms. Let's dive in and break it down step by step. In this problem, we are given an array of integers called nums and a value k. Our task is to find the maximum sum of any two numbers from the array such that their sum is less than k. If it's not possible to find such a pair, we return -1. Now, let's look at the format of the input and output. The input consists of the integer array nums, where the length of the array can range from 1 to 1000, and the elements can have values between -10,000 and +10,000. Additionally, we are given an integer k, which can range from 0 to 10,000. The output is a single integer, which represents the maximum sum of a valid pair, or -1 if no such pair exists. To understand this better, let's examine a few examples. In the first example, the input array is 34, 23, 1, 24, 75, 33, 54, 8, and k is 60. The output here is 58. This is because the pair, 34, 24, has the largest sum, which is 58, and it is still less than 60. Now, consider the second example, where the input is 10, 20, 30, and k is 15. The output in this case is -1, as there is no pair of numbers in the array whose sum is less than 15. Finally, let's look at an input where the array is 5, 1, 2, 10, 7, and k is 9. The output for this example is 8, because the pair, 5, 2, gives the largest sum, which is 8 and less than 9. Now, let's review the constraints and edge cases for this problem. The length of the array nums is guaranteed to be between 1 and 1000. Each element in the array can be as small as -10,000 or as large as +10,000. The value of k is between 0 and 10,000. For edge cases, it's important to note that if no pairs have a sum less than k, we must return -1. Similarly, if the array has only one number, we cannot form a pair, so the output should also be -1. For large inputs, such as arrays with 1,000 elements, our solution must be efficient. Additionally, we need to handle negative numbers correctly and account for cases where k is 0, as no sum can be less than 0 in that scenario, meaning the output should be -1. To begin, let's consider the brute force approach. The intuition behind this method is straightforward. We iterate through all possible pairs of numbers in the array and calculate their sums. For each pair, we check whether the sum is less than the given value, k. If it is, we update a variable to keep track of the maximum sum we've found so far. This approach is simple to implement, as shown in the provided code snippet. Here, we use nested loops to examine every pair, calculate their sum, and update our maximum if the conditions are met. However, this comes with a significant trade-off. Since we are checking all pairs, the time complexity is n squared, which makes this approach inefficient for larger arrays. On the other hand, it is space efficient with a space complexity of 1, since no additional data structures are used. While intuitive, this method becomes impractical as the input size grows, prompting the need for a more optimized solution. Now, let's focus on the optimized approach using sorting and the two-pointer technique. The insight here is that sorting the array allows us to systematically examine pairs without needing to check all combinations. By placing one pointer at the start of the sorted array and another at the end, we can evaluate sums in a controlled manner. If the sum of the two numbers is less than k, it means this pair is valid, and we shift the left pointer to explore larger numbers. If the sum is greater than or equal to k, we move the right pointer to explore smaller numbers. This approach avoids unnecessary checks by narrowing the range of possibilities with each step. The algorithm begins by sorting the array and initializing the left and right pointers. Then, while the pointers don't overlap, we evaluate the sum of the numbers at their positions. Depending on whether the sum is valid, we either update the maximum sum and shift the left pointer or move the right pointer to continue searching. This process ensures efficiency while systematically covering all potential pairs. The implementation of the two-pointer technique continues with the core logic. If the sum of the current pair is valid, meaning it's less than k, we update the maximum sum found so far and increment the left pointer to explore larger sums. Otherwise, when the sum is greater than or equal to k, we decrement the right pointer to test smaller sums. This process repeats until the pointers meet, at which point we return the maximum sum found, or -1 if no valid pair exists. In terms of complexity, the time cost is primarily driven by sorting, which takes n log n, followed by the linear traversal of the array using the two pointers, resulting in an overall time complexity of n log n. The space complexity remains 1, since no additional data structures are required. This approach is not only faster for large arrays compared to brute force but also intuitive to implement. However, sorting introduces a slight overhead, particularly for smaller input sizes, which is a minor trade-off for the efficiency gained in larger cases. An alternative solution involves using binary search to find the largest valid pair for each element after sorting the array. While binary search can be an effective tool, it introduces additional complexity in implementation and debugging compared to the two-pointer technique. Moreover, the overall time complexity remains n log n, as sorting still dominates, and binary searches for each element add further logarithmic overhead. Thus, this approach does not offer a significant advantage over the two-pointer method. Now, focusing on the chosen strategy, the two-pointer approach stands out as the most practical solution. It is easy to implement, avoids nested loops, and systematically eliminates invalid pairs. The combination of sorting and pointer adjustments ensures a balance between performance and simplicity. The key insight that makes this method effective is recognizing that sorting the array allows us to explore pairs more efficiently, saving time by narrowing the search space with each pointer movement. Finally, while the two-pointer approach introduces a small overhead due to sorting, this cost is far outweighed by the efficiency it provides for large inputs. Additionally, its simplicity and readability make it an ideal choice for this problem. By avoiding the complexities of binary search and the inefficiencies of brute force, this strategy offers a clear and effective solution. The key takeaway is that sorting the array enables systematic exploration of valid pairs, and the two-pointer technique ensures we find the maximum sum efficiently. In conclusion, the two-pointer strategy strikes the perfect balance between optimal performance and ease of implementation, making it the preferred approach for solving the two-sum less than k problem. To solve this problem, we need to find the maximum sum of any two numbers in the array such that their sum is less than the given value k. If no such pair exists, we should return -1. The first step is to fully understand the problem and its constraints. Here, the input consists of an array of integers and a target value k. The output is the maximum sum of any pair of integers that satisfies the condition, or -1 if no valid pair can be found. The constraints indicate that the array may contain both positive and negative integers, and its size can vary. This means our solution should be efficient enough to handle larger inputs. A brute force approach is our starting point. It involves iterating through all pairs of numbers and checking their sums. We begin by initializing a variable, max_sum, to -1. This will store the largest valid sum we find. Then, we use two nested loops to go through all pairs of elements in the array, ensuring that each pair is considered only once. For each pair, we calculate their sum and check if it meets the condition of being less than k and greater than the current max_sum. If the sum satisfies these conditions, we update max_sum with the new value. Once all pairs have been checked, the value of max_sum is returned. The brute force implementation looks like this. We initialize max_sum to -1, then use two nested loops to iterate through all pairs in the array. For each pair, we calculate their sum. If the sum is less than k and greater than max_sum, we update max_sum. Finally, we return max_sum. While this approach is straightforward, its time complexity is n squared, due to the nested loops, which makes it inefficient for large arrays. The space complexity, however, is 1, as no additional space is used. The main limitation of this method is its inefficiency for larger inputs, which is why we'll now explore a more optimized solution. To improve efficiency, we can use an optimized approach that combines sorting and the two-pointer technique. The first step is to sort the array in ascending order. Sorting ensures that smaller numbers appear first, which helps us systematically explore valid pairs. The time complexity of sorting is n*log n. Next, we initialize two pointers, one, called left, pointing to the smallest element at index 0, and the other, called right, pointing to the largest element at the last index. These pointers allow us to efficiently explore pairs without the need for nested loops. The main idea is to iterate through the array while the left pointer is less than the right pointer. For each iteration, we calculate the sum of the elements at the left and right pointers. If the sum is greater than or equal to k, we move the right pointer one step to the left to reduce the sum. If the sum is less than k, we check whether it is greater than the current max_sum. If it is, we update max_sum and then move the left pointer one step to the right to explore larger sums. After the loop ends, we return the value of max_sum, which will contain the largest valid sum found. The optimized implementation looks like this. First, we sort the array in ascending order. Then, we initialize the left and right pointers, as well as max_sum, which starts at -1. While the left pointer is less than the right pointer, we calculate the sum of the elements at these positions. If the sum is less than k, we update max_sum if the sum is greater than the current max_sum, and then move the left pointer to the right. If the sum is greater than or equal to k, we simply move the right pointer to the left. Once the loop completes, we return max_sum. This approach efficiently reduces the time complexity of the problem to O and log n, which is dominated by the sorting step, while the two-pointer traversal itself runs in O n time. The key insight behind this optimized approach is that sorting the array allows us to systematically explore pairs with the smallest and largest values, significantly reducing the number of pairs we need to check. The two-pointer technique is particularly efficient because it eliminates the need for nested loops, allowing us to explore all valid pairs in linear time after sorting. When considering edge cases, we need to account for scenarios such as arrays with fewer than 2 elements, where no pair exists and we should return -1. Similarly, if all pairs have sums greater than or equal to k, we also return -1. It's important to handle arrays with negative numbers carefully, as they can affect the sums. For example, in an array like -5, -2, 1, 3, with k equal to 0, valid pairs must be carefully identified. In terms of complexity, the total time complexity of this approach is O and log n, due to the sorting step, while the space complexity is O, 1, as we use the input array directly and require no additional data structures. With this optimized algorithm, we can efficiently find the maximum sum of pairs less than k, even for larger inputs. By combining sorting and the two-pointer technique, the algorithm achieves a scalable time complexity of O and log n, making it well-suited for real-world scenarios where the input size can be substantial. This approach ensures that we not only get the correct result but also do so in an optimal and resource-efficient manner. This solution leverages the two-pointer technique to efficiently find the maximum sum of any pair of integers in the array that is less than the given value k. 1. Sorting the array. The first step is to sort the input array. Sorting is essential to enable the two-pointer approach, which relies on the array being ordered to systematically explore possible pairs. 2. Initializing variables. The algorithm initializes two pointers, left at the start of the array and right at the end. Additionally, a variable max_sum is initialized to -1, which will store the maximum valid sum found during the iteration. 3. Iterating with two pointers. The while loop runs as long as the left pointer is less than the right pointer. This ensures all potential pairs are considered without revisiting already checked combinations. Calculating current sum. The sum of the elements at the left and right pointers is calculated. If this sum is less than k, it is a valid candidate. The algorithm updates the max_sum with the larger of the current max_sum and the current _sum. Adjusting pointers. If the current _sum is valid, less than k, the left pointer is moved one step to the right to explore larger sums. If the current _sum is greater than or equal to k, the right pointer is moved one step to the left to reduce the sum. 4. Returning the result. After the loop, the function returns max_sum. If no valid pair was found, max_sum remains -1, which is the correct return value for this scenario. This approach has a time complexity of O n log n due to the initial sorting step, with the two-pointer traversal contributing an additional O n. The space complexity is O 1, since no extra data structures are used. This makes the solution efficient and suitable for large input sizes within the problem constraints. This is the Java implementation of LeetCode problem number 1099, 2 sum less than k. The logic mirrors the Python implementation, using a two-pointer approach after sorting the array. Key differences include the use of Java's arrays.sort method for sorting, explicit type declarations for variables, and the math.max function to track the maximum sum. The implementation is efficient and concise, adhering to Java's syntax and conventions. Let's walk through the first example where the input array is 10, 20, 30, and k is 50. The array is already sorted, so we start by initializing three variables: left at the beginning of the array, right at the end, and max_sum set to -1. Now, we look at the pair formed by the elements at the left and right pointers, which are 10 and 30. Adding these gives us a current sum of 40. Since 40 is less than 50, it's a valid candidate. We update max_sum to 40 and move the left pointer one step to the right to explore larger sums. Next, the left pointer moves to index 1, giving us the pair 20 and 30. The sum here is 50, which is not less than k. So, we move the right pointer one step left to try smaller sums. At this point, the left and right pointers meet, and the loop ends. The maximum sum we found that's less than k is 40. Now, let's consider the second example with the input array 1, 8, 12, 15, and k set to 10. The array is already sorted, and we initialize the same variables, left at 0, right at the last index, and max_sum at -1. Looking at the first pair, 1 and 15, their sum is 16, which is greater than or equal to 10. To reduce the sum, we move the right pointer one step left. Now, the pair becomes 1 and 12, with a sum of 13. Again, this is not less than k, so we move the right pointer again. The next pair is 1 and 8, with a sum of 9. This time, 9 is less than 10, so we update max_sum to 9 and move the left pointer to look for larger sums. The left pointer moves to index 1, but now it meets the right pointer, and the loop terminates. The maximum sum we found in this case is 9. In the third example, we're given the array 5, 2, 9, and k set to 7. After sorting, the array becomes 2, 5, 9. We initialize left at 0, right at the last index, and max_sum to -1. Looking at the first pair, 2 and 9, their sum is 11, which is greater than or equal to k. To explore smaller sums, we move the right pointer one step left. Now, the pair is 2 and 5, with a sum of 7. This is equal to k, so it's not valid, and we move the right pointer again. At this point, the right pointer moves to the same position as the left pointer, and the loop ends. Since we didn't find any valid pair with a sum less than k, the result here is -1. The algorithm consistently applies the two-pointer approach to maximize efficiency. By sorting the array first, we can systematically check pairs and adjust the pointers to explore smaller or larger sums as needed. This avoids unnecessary computations and ensures we only consider valid candidates. Across these examples, the approach demonstrated how to find the maximum sum of two numbers less than k, or determine when no such pair exists, all while maintaining a time complexity of O and log n, due to the sorting step. When analyzing the time complexity of our solution, we can break it down into two main steps. First, we sort the input array. Sorting an array of size n using efficient algorithms like timsort, which is used in Python, takes O and log n time. This is the most computationally expensive part of the solution. Next, we use the two-pointer technique to find the maximum sum of two elements that is less than k. In this step, the left and right pointers traverse the array, with each pointer moving at most n steps combined. This traversal is linear, taking O, n, time. However, since O, n log n, is asymptotically larger than O, n, the overall time complexity of the solution is dominated by the sorting step, resulting in a total time complexity of O, n log n. Now, let's consider the space complexity of the algorithm. The solution operates directly on the input array and sorts it in place, meaning no additional memory is allocated for sorting. Furthermore, the algorithm uses only a constant number of extra variables such as left, right, max_sum, and current_sum, which require O1 space. Since the algorithm does not rely on any additional data structures or memory allocations, the overall space complexity remains O1. To better understand the efficiency of our solution, let's analyze the best, average, and worst case scenarios. In the best case, where the array might already be sorted or nearly sorted, the algorithm still requires sorting the array explicitly, which ensures the time complexity remains O n log n. On average, the same operations are performed regardless of the input's distribution. Sorting still takes O n log n, and the two-pointer traversal takes O n, so the overall time complexity is O n log n. Even in the worst case, where the input array is in reverse order or poorly structured, the algorithm does not change its approach. Sorting and the two-pointer traversal are still required, resulting again in a time complexity of O n log n. This consistency demonstrates the robustness of the algorithm. It's also helpful to compare this optimized solution to a brute force approach. The brute force method involves iterating through all possible pairs in the array, checking their sums, and ensuring that the sum is less than k. This requires two nested loops, leading to a time complexity of O n squared. While the space complexity of the brute force approach is also O1, the time complexity is significantly worse for larger inputs. In contrast, the optimized solution sorts the array in O n log n, and uses the two-pointer technique in O n, achieving a much better time complexity of O n log n. The space complexity remains O1, just like the brute force approach, as no extra data structures are used. This makes the optimized solution significantly faster for large datasets. Finally, let's validate the time complexity mathematically. Sorting an array of size n takes O n log n, because efficient sorting algorithms, like timsort, use a divide-and-conquer strategy. The two-pointer traversal, where both pointers move through the array in a single pass, adds another O n. When we combine these, the total time complexity becomes O n log n plus O n, which simplifies to O n log n, since the sorting step dominates. As for space complexity, the algorithm sorts the array in place and uses a few auxiliary variables, resulting in a constant space requirement of O1. This mathematical breakdown confirms the efficiency of our approach. When solving this problem, there are a few common mistakes to watch out for. First, in brute force approaches using nested loops, it's easy to accidentally compare the same element with itself, such as calculating a underscore I plus a underscore I instead of a underscore I plus a underscore j where I is not equal to j. This can produce incorrect results, especially when distinct pairs are required. The fix is straightforward. Ensure that the inner loop starts at I plus 1 to avoid duplicate comparisons. Another mistake occurs when using optimized approaches, like hash maps or two-pointers, without accounting for duplicate values. This can lead to overcounting pairs. A good practice is to add checks that skip over duplicate elements, particularly when working with sorted arrays or hash maps. Developers also sometimes misinterpret constraints, like confusing some less than k with some exactly equal to k, leading to flawed logic. Always take the time to carefully read the problem statement and fully understand the boundaries and requirements. Lastly, failing to optimize for large input sizes is a frequent issue. While a brute force O n squared solution might work for small arrays, it's crucial to switch to more efficient methods, such as the two-pointer or hash map approach, when dealing with larger datasets. Always consider time complexity and adapt your solution based on the input size constraints provided in the problem. Edge cases are another area where mistakes often occur. For example, overlooking scenarios like empty arrays, single-element arrays, or arrays where no valid pair exists can lead to bugs in your solution. To avoid this, make it a habit to explicitly test for edge cases during your implementation. From an interview perspective, it's important to recognize patterns. Many array problems, such as two-sum or k-sum variations, rely on similar strategies like two-pointer techniques or hash maps. By mastering these patterns, you'll be better equipped to tackle related problems quickly and effectively. Additionally, clarity in communication is key. Interviewers appreciate when candidates start by explaining a brute force solution, highlight its limitations, and then transition to an optimized approach. This demonstrates both critical thinking and problem-solving ability. It's also helpful to address how your solution handles constraints, like large input sizes, edge cases, and special conditions. This shows interviewers that you think through all aspects of a problem. Finally, be prepared to discuss time and space trade-offs. For instance, while a hash map can significantly reduce time complexity, it does so at the cost of increased space usage. Being able to justify these trade-offs can leave a strong impression on your interviewers. This problem shares similarities with several related problems you might encounter on LeetCode. For instance, the classic two-sum problem, which is LeetCode number 1, asks you to find two numbers that add up to a specific target. Another is the three-sum problem, LeetCode number 15, which involves finding unique triplets in an array that sum to 0. There's also subarray sum equals k, LeetCode number 560, where you need to count the number of subarrays that add up to a given value k. Lastly, k-diff pairs in an array, LeetCode number 532, focuses on counting unique pairs where the difference between the elements is exactly k. When tackling these problems, there are a few alternative approaches you can consider. The two-pointer technique is a popular method. It involves sorting the array, then using two pointers, one at the start and one at the end, and adjusting them based on whether the current sum is less than, greater than, or equal to the target. This approach runs in O, n log n, time due to the sorting step, followed by O, n, for the traversal. It's faster than brute force but requires sorted input. Another option is the hash map method, which stores the difference between the target and the current element, allowing for quick lookups to find complements. This is an O, n, time solution, though it's more space-intensive. Finally, there's the brute force approach, which checks all possible pairs. While simple, it's highly inefficient with a time complexity of O, n squared, making it unsuitable for larger inputs. Each approach has its trade-offs, so understanding when to use each one is crucial for solving these types of problems effectively. Great job completing this problem. In summary, we tackled the two-sum less than k problem using efficient techniques like sorting and two pointers to optimize our solution. Remember the key concepts we discussed, and keep practicing similar problems to strengthen your skills. Thanks for joining, and see you in the next walkthrough. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!